Have you ever had a smell just hit you so perfectly that it's like a Dementor from Harry Potter? But, instead of stealing your joy, it just perfectly extracts this one super specific happy memory? Like
Yes.
maybe it's the scent of, I don't know, Old Spice and sawdust from your grandfather's garage?
Right, or something you haven't thought about in decades.
Exactly. That instantaneous, visceral reaction. It's just proof that the sense of smell is the stealth superpower of the human body.
It really is. That whole phenomenon
Uh,
highlights one of the most sophisticated yet, well, profoundly underappreciated sensory systems we have.
right.
We tend to focus so much on sight and sound, but olfaction, it holds a direct, non-stop ticket to our deepest emotional core.
It's the silent partner to everything else, and today we are giving it the spotlight. Welcome to the deep dive. We're taking a massive stack of research, specifically an exhaustive literature survey compiling data from 69 unique scientific sources to understand that complete journey, from a single floating molecule all the way to a deep integrated memory.
And our mission here is really to synthesize these findings, to explain the core complexity of the olfactory system. Because this system, it's truly a bridge. It uniquely integrates detecting a chemical stimulus with deep emotion, memory, and behavior, all through these distributed neural circuits.
The sensory fast lane to the limbic system.
Exactly.
Okay, so let's unpack this journey. Let's start right at the entrance with the molecular gatekeepers. Because when you look at the pure numbers, there's a massive puzzle here. We only have about 400 functional olfactory receptors, or Rs, in our nose.
Right.
But somehow we can distinguish millions, maybe more, different odors. How on earth does that math work out?
Yeah, that's the big question.
It feels like trying to paint every color in the visible spectrum using just like 4 tubes of paint.
It's an absolutely elegant solution, and it's what's called the combinatorial recognition strategy.
Okay, combinatorial.
The key realization is that you just don't need a dedicated, unique receptor for every single smell in the world. That would be wildly inefficient.
So instead, each receptor has to multitask.
Precisely. Each of those 400 receptor types is what we call promiscuous.
Yeah.
It binds to multiple different odorants, but with, varying degrees of affinity. And crucially, any single odorant molecule, it activates multiple different receptors at the same time.
So if I smell a rose, the input isn't just one signal. It's more like a specific chord being played across those 400 strings.
That is the perfect analogy.
Like low activation on receptor 10, high on receptor 50, medium on 101, and a lemon is just a slightly different chord.
Exactly. The odor's identity isn't in which single receptor fires. It's represented by a specific high-dimensional activation pattern across the whole set. It's chemical code. And that complexity is what overcomes the limitation of only having 400 basic sensor types.
A genius compression algorithm.
It really is.
That makes so much sense. Now let's drill down on the receptors themselves, because this is where it gets really specialized. We know these olfactory receptors are ours. They belong to this massive family of G protein coupled receptors, GPCRs, the things that regulate basically everything in the body. But the sources show that olfactory receptors, they operate differently from their cousins.
They absolutely do. And it really took the sophistication of cryo-electron microscopy to reveal this.
Okay.
A study in Nature Communications looked at the structure of an olfactory receptor, or R52, and found this totally unique activation mechanism.
What was the difference structurally?
The difference is in the movement of the core structure when the odor molecule actually binds to it. A specific part, transmembrane domain 6, or TM6,
Yeah.
it undergoes this unusually large inward movement.
And what does unusually large mean here on a molecular scale?
We're talking about a displacement that is roughly 3 times greater than what you typically see in other Class A GPCRs. The implication is huge. This massive shift is necessary because the olfactory system have to accommodate an incredible diversity of molecular shapes.
Right.
Unlike, say, a hormone receptor that only needs to bind one specific molecule, these receptors have to be flexible enough for hundreds of shapes. And that big displacement is the architectural solution.
It's like the hinge on the olfactory receptor door swings 3 times wider than any other door in the body, just to let in more variety.
A great way to put it.
So now that we know how the receptor works, what about the molecule itself? What even determines if something can smell in the first place?
Fundamentally, it's about physics and transport. The sources detail a surprisingly simple set of criteria, kind of rule of 3 a compound has to satisfy.
Okay, lay out the rules for us.
First, the molecule must be volatile enough to enter the air and, float up your nose. That's the obvious one.
Sure.
Second, And this is the counterintuitive part. It has to be non-volatile enough to get through the aqueous mucus layer that coats your olfactory epithelium.
Ah, so it has to be light enough to fly, but also heavy enough to swim.
Precisely. And third, it has to be hydrophobic enough to basically jump out of that watery mucus and into the fatty receptor pocket.
That dual requirement, that feels like the hidden secret of smell.
It is.
And that brings us to the ultimate, just staggering question.
Yeah.
What is the total universe of things that can smell?
This is the mind-bending part. Based on predictive modeling, oh wow. Fact, really, because the main barrier is that physical transport, not the receptor itself. They could predict the scale. They found a simple predictive rule molecular weight between 30 and 300 Daltons, fewer than 3 heteroatoms. That captures 96% of odor accuracy.
Wow, that seems like a tiny chemical fingerprint to capture almost all smells.
It is. But when you apply those rules to known organic chemistry, the prediction it scales up dramatically.
Yeah.
At least 40 billion small organic molecules are predicted to be odorous.
40 billion.
40 billion. That's 6 orders of magnitude higher than what anyone used to think.
That is incredible, from just 400 basic sensors.
Wow.
It's like having 4 notes, but the number of symphonies you can write is virtually limitless. Okay, so let's move the signal from the nose and into the brain. How does the brain maintain any kind of order amidst all this chemical chaos?
The organization starts immediately, right at the olfactory bulb. The sensory neurons that express the same receptor type, they don't just scatter their signal. They all converge onto these discrete spherical processing centers called glomeruli.
So if receptor 5 is activated, every single signal from every receptor 5 neuron goes to the same tiny spot in the bulb.
Yes. This convergence is key. It forms a precise topographic map. Odor space is literally translated into a spatial pattern of activated glomeruli. And what's fascinating is that this organization persists with remarkable precision across individuals.
So even though my set of 400 receptors might be a bit different from yours, the map in our brains is basically the same.
Like every city using the same subway schematic. Yes.
This structure leads us right to the most powerful feature of smell. It's linked to emotion and memory. We learn in school that all other senses, sight, hearing, touch, they all go through the thalamus, the central relay station, before hitting the emotional centers.
Right.
Smell just skips the middleman entirely.
That is the critical distinction.
Yeah.
It gives olfaction its profound emotional power. The olfactory bulb projects directly to the amygdala, the brain's fear and emotion hub, without that thalamic relay.
A privileged high-speed pathway. What's the evolutionary advantage there? Why does smell need to get to the emotion center faster than sight or sound?
Survival. When we smell something, especially something dangerous, a gas leak, spoiled food, smoke, the brain has to determine its valence before its precise identity.
Valence meaning good or bad.
Good or bad, safe or dangerous. Functional imaging shows the amygdala just lights up for aversive or bad smells. The amygdala neurons are encoding whether it's pleasant or unpleasant, often before the higher cortex is even fully processed what the chemical is.
So the instant reflexive recoil you get from a horrible smell, that's the amygdala yelling danger, before your cortex can whisper, oh, that's just rotten garbage.
Exactly. And the hippocampus, the brain's memory librarian, is what links those powerful nostalgic odor memories we started with. It integrates the smell with context, supporting that episodic memory.
But the memory only sticks if the emotion is there, right?
That's the link. A study showed that with bilateral amygdala damage, you can still perceive odors just fine, but your ability to consolidate new olfactory memories is gone.
So you can smell it, but the binder that ties the smell to the memory is broken.
The binder is broken, exactly.
Okay, we have to clarify the difference between smell and a flavor. When I eat, say, a piece of dark chocolate, and I get notes of cherry and smoke, what am I actually using?
You are primarily experiencing retronasal smell.
Retronasal.
Right. Orthonasal is what we think of as smelling odorants entering through the nose when you sniff. Retronasal is when odorants from food in your mouth travel up the back of your throat to the nasal cavity while you're chewing.
Ah.
Flavor is the fusion of taste, texture, and that retronasal smell.
So when a chef talks about mouthfeel or a sommelier talks about the finish, they are relying entirely on that internal route.
They are. And the brain processes these two routes differently. To express a preference for a flavor liking that chocolate retronasal odors need the gustatory cortex to combine all the inputs.
So just smelling something from the outside doesn't.
Orthonasal odors bypass that requirement.
Yeah.
Your brain treats the smell of coffee before you drink it, and the smell of coffee while you're drinking it, as two fundamentally different realities.
Which explains why food is tasteless when you have a cold. You can only use orthonasal smell.
Precisely. Your flavor system is offline.
Let's shift now to how we actively use this sense. We often treat smell as passive, right? You just breathe in. But the sources reveal it's an incredibly active and motivated process.
It's a motor behavior. Sniffing is not just breathing. It is actively regulated by a reward and motivation system. Research has made this connection really clear, showing that dopamine release into the ventral striatum, a key reward area, is directly coupled with sniff bouts.
Dopamine, the reward chemical, it actually drives how intensely we sniff.
It does.
So if I'm actively looking for a rewarding smell, like tracking down fresh-baked cookies, my brain literally adjusts my breathing to be better at it.
Absolutely. When you're motivated to find a rewarding odor, that dopaminergic signaling controls the intensity and frequency of your sniffing. You automatically sniff harder and more often.
Like the targeting scanner on a predator drone increasing resolution when it detects heat.
It's a perfect analogy. The brain is regulating the nose's sensitivity based on your motivational state.
That's amazing. Okay, before we get to the clinical side, we have to touch on the second sensory system in the nose, the one for sharpness or pungency.
Right, which isn't technically smell at all. That's trigeminality. Many odorants don't just activate the olfactory bulb, they also activate the trigeminal nerve, the main sensory nerve of the face.
And that creates sensations like burning or coolness or irritation.
Exactly, distinct from the actual perceived odor.
What's a good example of the difference?
Think about cinnamon. The sweet brown scent of cinnamon, that's olfaction. The sharp, hot feeling of cinnamon oil on your tongue, that's trigeminality.
Ah,
It
okay.
involves activating ion channels like TRPV1, that's the capsaicin receptor that makes chili peppers hot, and TRPA1, which is activated by things like formaldehyde or tear gas.
So it's the body's built-in chemical warning system running in parallel.
Precisely.
Finally, let's talk clinical implications, especially with aging and health. We hear that smell declines with age. How significant is this, and what does it tell us?
It's a very significant decline, and it's an extremely strong health indicator. Olfactory dysfunction, or hyposmia, starts around age 60 and accelerates. For people over 75, a majority 56% have it. Males seem to be more affected.
But it's not just a benign sensory issue.
Not at all. Yeah. The biggest implication is that it acts as an early warning system for neurodegeneration.
A biomarker.
A powerful one. Impaired olfaction correlates strongly with smaller brain volumes in the hippocampus and entorhinal cortex. Crucially, studies show it predicts a faster rate of cognitive decline even before someone develops dementia. It signals issues brewing years in advance.
Wow. So the underappreciated sense of smell becomes a critical piece of preventive medicine.
It should be.
And in the modern world, we have to talk about post-viral recovery, which became so common with COVID-19. What do we know about getting that sense back?
Well, estimates suggest 10 to 15% of patients suffer persistent impairment and recovery. It proceeds in stages. The intermediate stage, stage 2, is often characterized by parosmia.
That's the smell distortion, isn't it? Where familiar things like oranges or toothpaste smell like burnt rubber or rotten meat.
It's incredibly distressing, yes, but it's often a sign that the nerves are regenerating and just connecting incorrectly.
So what can you do?
The good news is we can intervene. The recommended strategy is smell training.
Like physical therapy for the olfactory bulb.
Essentially, it involves focused, repeated sniffing of 4 distinct common odors, usually rose, lemon, clove, and eucalyptus, twice a day. This active engagement substantially accelerates recovery. It drives neuroplasticity and helps restore functional connectivity in the primary olfactory cortex.
You're forcing the brain to correctly remap those confused signals.
You are.
This has been a truly comprehensive deep dive. I mean, we started with 400 receptors and ended with 40 billion potential smells. So what are the 3 foundational takeaways for our listener?
I think you have to start with the incredible efficiency of the biological code.
Yes. First, the code. The human nose uses a brilliant combinatorial code with only 400 receptors to encode billions of potential odors. It's just biological data compression at its finest.
Second, the emotional impact. Olfaction is uniquely tied to memory and primal emotion via that direct amygdala projection. That gives smell its potent, often unconscious, power.
And finally, the action and indicator. Smell is an active, motivated process. Your sniffing is regulated by dopamine, and its decline can be a critical health indicator for neurological aging.
And yet, despite all we know, the single biggest unsolved challenge is the structure-odor relationship, or SOR. We still cannot reliably predict how a molecule will smell just by looking at its chemical structure.
And you see this paradox perfectly with enantiomers, right? Those mirror image molecules with identical parts.
They should smell the same. Logically, they should, but fewer than 5% of them actually do.
Wow.
It just shows our current computational models are fundamentally failing to predict perceived quality. We're missing a critical piece of that spatial puzzle.
Which leads us to our final provocative question for you to think about. We know that genetic variation in your 400 olfactory receptors only explains about 10 to 20% of why you perceive odors differently than your neighbor. So what cognitive, experiential, or epigenetic factors account for the other 80% of your unique olfactory world?
Something to contemplate the next time you take a deeply satisfying, dopamine-motivated sniff of your morning coffee.
Thank you for joining us for this deep dive into the molecular secrets of the nose. If you want to keep gaining knowledge quickly and thoroughly, make sure you subscribe to the deep dive. We'll see you next time.